talk about my little experience in the field of thin film based solar cell or thin film photovoltaics. So this will be the basic outline of my talk. So first, I'll be discussing about I'll give a brief introduction to thin films. So there I'll be little bit discussing about the basic definition of thin films and what is the growth mechanism. Then I will go through a few applications of thin films, thin film technology. Then I'll be focusing more on the thin film based solar cells, which is basically a cost effective way for the energy production. And then I'll be discussing about the various deposition techniques which can be used to deposit the different layers in this thin film based solar cell. I'll be focusing more on the vacuum based deposition techniques, that is evaporation and sputtering. And finally, I'll conclude my presentation by giving you a brief overview of the current status of the thin film based photovoltaics. So let us start with the brief introduction to thin films. So the very basic definition of thin films lies in its birth process. So it has little to do with the thickness of the thin films. The thickness of films can range between few nanometers and it can go up to few tens of micrometers. But the definition of the thin films or the exotic properties that is exhibited by the thin film is because it has been grown ab initio by the random nucleation and the growth processes that the individually condensing or the reacting atomic species go through on a substrate. So the growth has to start from ab initio. That means atom by atom or the molecule by molecule, the growth process has to occur. Then only we can observe the exotic properties that is exhibited by the thin films. And as the birth process suggests, so the thickness of the films can range between few nanometers to few tens of micrometers. So what is the advantage of using the thin films? So the thin film techniques, basically there can be other techniques which are thin in their thickness. For example, the thick film techniques, we can get them by thinning the material or by screen printing or by electrophoresis or by laser ablation, but they will not exhibit the exotic properties which is shown by the thin films. So the thin films exhibit the exotic properties because of their certain deposition parameters, because of their ab initio growth. And the properties can be tuned by changing the deposition parameters in a very controlled manner. And since it involves the atom by atom or the molecule by molecule growth, that's why we can have a very relaxed phase diagram. Here I've given one example for the growth of indium gallium nitride thin films. Basically, it is an alloy between indium nitride and gallium nitride. So when we mix these two samples, that is indium nitride and gallium nitride, through any solid state synthesis method, we will get a phase separation. We will not be able to get the alloy in the entire composition range. But when we try to grow it ab initio, that means by atom or by molecule growth process, in that case, we are able to get the composition starting from 18% to around more than 80%. So that is what is the beauty of the growth using the thin film techniques. We can get a relaxed phase diagram. There is no phase separation. In this case, there is no secondary phase involving indium nitride or gallium nitride. We can get the complete composition of this alloy in the entire from 0 to 100% almost we can get it. Another important property that we can see here is the optical properties. For example, here we have shown two transmittance spectra for TiO2 films. The first one has been grown by a thick film technique, that is what is screen printing. And here we can see the transmittance. It almost looks flat and it gradually increases. But when you see the TiO2 thin films optical spectra, here you can see that this has been grown by sol gel based spin coating. Here the nice interference fringes, you can see it in the transmittance spectra. So this is the difference between the properties, the optical properties of the thin films and the thick films. It is because of the thin film interference phenomena when it is exposed to the light. So basically, what is the growth mechanism in this case? So it is a step-by-step growth process. So first of all, the atoms are adsorbed on the substrate surface, and they are called as the add atom. And the add atoms are having certain mobility, and due to that mobility, it is guided by the thermodynamics of the process, and they start to aggregate. And after aggregation, if the Gibbs free energy is crossing certain critical level, the nucleation will start to begin. Nucleation will start, and due to this nucleation, the size of the particles will slowly increase. First, we will have the nanoparticle growth, and then these nanoparticles will coalesce together to form the bigger islands or bigger grains. And finally, the missing channels will be filled. That is what is called as the filling of the channels, and ultimately will result in a continuous formation of the films. So it is a atom by atom growth process. We started with individual atom being condensing on the substrate surface. Gradually, it is governed by the thermodynamics of the process, and they form the grain, and then the filling of the channels takes place, and the resultant is a continuous film. So there are different growth mechanisms which has been prescribed in the literature for the thin film growth process. The first one is called as the island type of growth. In this case, the cohesive force between the film atoms is very, very strong compared to the adhesive force between the film atoms and the substrate. So as a result, the atoms, they form individual island in this case, and the resultant is a nanocrystalline film. So in this case, the corresponding crystallinity is very poor because of the strong bondage between the film atoms than that of the substrate. So here the diffusion is very, very slow. The other extreme is the layer by layer growth. In this case, the force of adhesion between the film atoms and the substrate is very, very high. There is a strong bond between the film atoms and the substrate. So the resultant is the formation of the layer by layer structure. And by this, the highest crystalline films can be grown. But the most popular or the most acceptable growth technique is a mixture of this island growth and the layer by layer growth, which is called as the mixed growth or the Stransky-Krasnov growth. So initially, it is because of the strong adhesion between the film atom and the substrate surface, the layer by layer growth takes place, and after some time, the island formation takes over the growth process. So in most of the cases that we deal with in our regular experiments, it is involving the mixed growth mechanism. So let me show a few applications of the thin film technology. It has got many applications, including the high-tech areas and the day-to-day life applications. For example, biotechnology, AMI suppression, sensors, as it was discussed in the previous session yesterday, photovoltaics, laser mirror coatings, nuclear reactor windows, stealth technology, electrochromic windows, self-cleaning windows. These are the high-tech areas in which the thin films have got applications. In addition to that, in our day-to-day life, there are many common areas of applications of the thin films. So there are, for example, in the watches, we are having this thin film coatings, spectacles, we are having these coatings, automobile, corrosion resistance coatings, hard coatings on machine tools, and including few decorative coatings on toys and household appliances. But for today's talk, I will be focusing on the thin film based photovoltaics, where we convert the solar energy to electrical energy. So let me give a brief introduction to the solar cells, and then I will switch over to the thin film based solar cell. All of us know that solar cells are basically, they convert the light energy to the electrical energy, and the basic structure in case of thin film based solar cells, it contains a PN junction. And the PN junction is used for the purpose of the separation of the charge carriers which are produced by the light. Suppose we are having the, we have to choose a semiconductor for which the band gap is such that it can absorb all the light that is coming from the sun, and when it will absorb the light, it will generate the charge carriers, that is the electron hole pairs will be generated, and that happens in the absorber layer of the thin film based solar cell. And the next target is to separate, because the electron hole pair will always tend to recombine. So our next target is to effectively separate the electron hole pairs without allowing them to recombine with the help of a PN junction, because all of us know that the PN junction provides a built-in potential, and with the help of this built-in potential, we are going to separate the charge carriers to the extent which is possible and allow them to transmit it to the, allow them to go through the back and the top contact so that we can get the output voltage. That is what is the basic mechanism of the thin film based photovoltaics. So let us see it schematically. So this is the flat band diagram of a PN junction. So this is the p-type layer, this is the n-type layer, and here we can see the Fermi level is equilibrating at the junction region, and when it is shined by light which is having energy more than the band gap of this particular semiconductor, so what will happen? Initially the electron hole pairs will be generated. The electrons will go from the valence band to the conduction band, and since it is at a higher potential, the electrons can easily roll down from the p side to the n side. Similarly, the holes can easily go up from the n side to the p side. So because of this flow of the charge carriers from p side to n side or n side to p side, the minority charge carriers, because of that, one built-in potential is developed, which one potential is developed, and because of that, which reduces the already built-in potential. And this can happen up to certain length. That is what is called as the diffusion length. This diffusion length, after this diffusion length, the electrons and holes will start to recombine. And this is related with the corresponding diffusion time or the carrier lifetime by the relation L equal to root over of d tau, where d is the diffusion coefficient and tau is the lifetime of the carrier. So after this time or after traveling this much distance, they will recombine with the corresponding holes or the electrons. So the region of interest in the solar cell, PN junction based solar cell, is this particular width, that is Ln W plus Lp. Lp is the diffusion length for the hole, Ln is the diffusion length for the electron, and W is the depletion width of the PN junction. So in this region, whatever is the electron hole pair, they can be separated and they can be collected across the external circuit. So what happens in this case? So initially, because of this built-in potential is reduced, the drift current flows from the P side, to N, from the N side to P side. And because of the reduction in the built-in potential, the diffusion current flows from the P side to N side. So as a result, we achieve two kinds of current. One is the diffusion dark current, and other one is the light generated current, which is a constant, which is not dependent on the voltage. When we add these two currents, we'll get the corresponding characteristic, the IV characteristic of the solar cell. And this is the corresponding equation. So this part is the dark current, and this part is the constant light generated current. It depends only on the intensity of the light and the band gap of the semiconductor. So with this little introduction, let us switch over to the basic construction of a thin film based solar cell. It is having different layers. So this is a brief schematic of the thin film based solar cell. So we are having two contacts here. This is the top contact and this is the back contact. Normally in the substrate geometry, the back contact is opaque. Mostly it is metal, and the famous, the more popular metal contact which is used is molybdenum because of the CIGS technology. Then remains the observer layer, which is the main portion of the thin film based solar cell, which can be cat telluride, copper, indium, gallium sulfide, copper, zinc, tin sulfide, etc., and many more observer layers. I have just given few examples here. Then remains the window layer, whose thickness is a little bit smaller compared to, little bit less compared to that of the observer layer. And finally, we are having a transparent layer, which is going to act as the top contact, because light has to come from the top, so it has to be transparent, and this band gap has to be smaller. Sorry, this band gap has to be larger compared to this band. So EG1 has to be larger compared to EG2. EG2 is the band gap of the observer layer, and EG1 is the band gap of the window layer. So the light has to pass through the top contact, window layer, and finally it should reach the observer layer, and then only it can generate the electron hole pairs in this particular layer. And typically the band gap EG2 is roughly around 1.5 electron volt, where it can absorb almost all the radiations which is coming from the sun. So let us discuss briefly about the different layers, and then we'll go to the different deposition techniques. So first one, as I told, the substrate on top of which we are having the contact, which is going to act as the back or the top electrode. And actually the substrate can have two different configurations. One is called as the superstrate configuration. Depending on the type of observer layer and the deposition techniques that we use, we can choose either the superstrate configuration or the substrate configuration. In the superstrate configuration, which is given here, in this case, light is going to pass through the substrate. So naturally, the substrate has to be transparent. So here we are going to use some kind of transparent conducting oxide, like the tin doped indium oxide as the one of the transparent conducting oxide, through which light can pass through it. Then the window layer, and then the then finally we are having the observer layer. And finally at the bottom we are having the corresponding back contact, which can be of any kind of metal, which having correct work function to match with that of the observer layer. Whereas the more conventional approach is to go with the substrate configuration. The superstrate configuration is mostly used for the cat telluride based solar cell, whereas for the CIGS or other type of solar cell, we go with the substrate configuration. In this case, we start with a glass substrate, and we coat the opaque metallic layer on top of it, then the observer layer, then the window layer, then the buffer layer, and finally we are having the transparent conducting oxide on top of it. So substrate configuration, the light is coming from the top across the on top of the glass substrate, whereas in the case of superstrate configuration, the light is coming directly on the glass substrate. That is what is the difference in the geometry of the substrate and superstrate configuration. And depending on the deposition techniques or the type of material that we are going to use as the observer layer, we can go for substrate or the superstrate configuration. Then comes, there are few important properties of the substrate. We cannot choose any substrate which we feel like. It should be mechanically stable, so that the cell has to be stable. It should not be very much fragile. The thermal expansion coefficient should match with that of the layer which is being coated on top of it. It should be inert during the device fabrication, and most importantly, it should form an ohmic contact. It should not form a Schottky barrier with the observer layer. Then coming to the transparent conducting oxide, which is going to act as the top contact layer in the solar cell, and mostly the transparent conducting oxide are the degenerate semiconductors. So in this degenerate semiconductors, what happens is that the impurity levels are very high, so that the impurity band merges with that of the conduction band or the valence band. As a result, it is having very high electrical conductivity. But together with that, it retains the high transparency, particularly in the visible region. And if you take the typical transmittance spectra of a suppose this is lambda of a transparent conducting oxide, mostly what happens is that in the infrared region, this is the visible region, so there is high transparency in this region. In the infrared region, due to the large number of charge carriers, free carrier absorption takes place. So it will start to absorb in the infrared region, which must be avoided. So we need to have a TCO which is having high electrical mobility, electron mobility, and which can be achieved by increasing the crystalline quality of the films, so that we can avoid this kind of free carrier absorption in the infrared region. Remember, this is the top contact layer, so light has to pass through it. It should not be absorbed by the particular layer. So to avoid that, we should have a TCO which is having high electron mobility, which is really a challenging task. The commonly used TCOs, the typical conductivity is around 10 to the power minus 4 ohm centimeter, and the transparency is usually more than 80%. So these are the few examples: tin doped indium oxide, fluorine doped indium oxide, aluminum doped zinc oxide, or indium doped zinc oxide. And out of this AZO is more cost effective because of the huge increase in the price of indium in this case. So the AZO contact layer is much more popular than the rest of the TCOs. Then coming to the window layer, as we have discussed, the main function of the window layer is to form a PN junction with the observer layer, and it should be having very high band gap, so that whatever light is coming through, it should pass through the window layer and it should be able to reach the observer layer. And together with that, it should be as thin as possible, because if it is very thick, then automatically the absorption of the photons will take place in the window layer, and also the series resistance of the device will also increase. And it should have a good lattice match with that of the other layers. Typically, cat sulfide is used as the window layer in many of the chalcopyrite based observer layers. And because of the concerns regarding the cadmium toxicity, the improvement is required, or the alternative window layers are required, and till some other window layers are being researched. For example, zinc sulfide or zinc oxysulfide, zirconium, gallium sulfide, all these things are being researched, so that we can replace effectively the window layer from cadmium sulfide. And finally, we are having the most important layer, which is the base of the solar cell device, that is the observer layer, where the photo generation and the charge separation takes place. And these are the basic characteristics of the observer layer. First of all, it should have the proper band gap, and it should be a direct band gap semiconductor, so that the number of electron and holes which are generated will be much more. There will be no loss in terms of the heat. Whatever energy is absorbed by the material, it should be in the form of electron hole production, not as phonons. And another important criteria, it should have high absorption coefficient of the order of 10 to the power 5 per centimeter. Then only it can absorb maximum light from the source. Then it should be able to effectively convert the light into the electron hole pairs, which is called as the quantum efficiency. It should have long diffusion length, because as we discussed, the efficiency depends on the diffusion length of the electron and hole. More is the diffusion length, more will be the effective separation of the electron hole pairs. Same is the case with the recombination velocity. It should be very, very low. and it should be forming a good electronic junction with the other compatible material for the window layer. There are a few basic examples here. I have shown it. So copper indium sulfide selenide, CIGS, cat telluride, copper zinc tin sulfide or selenide. They are the typical efficiencies of this layer, and there are many other cost-effective absorber layers are also available. So the major demerit of this ternary and quaternary absorber layers is the controlling of the stoichiometry. It is very difficult to control the stoichiometry except cat telluride in this kind of ternary and quaternary alloy absorber layer. So people are looking for different other alternatives to replace this absorber layer. The typical examples are antimony sulfide selenide, tin sulfide selenide, and few oxide also, like copper oxide, all is also being looked after to replace this quaternary and ternary semiconducting absorber layers. Now let us go to the deposition techniques which are widely used for the fabrication of the thin film based solar cell. As we know from the yesterday's discussion also, there are two basic type of deposition techniques. One is the vacuum based technique, and another one is the through the chemical route. Vacuum based technique, it is a one-time investment, but they need high maintenance. But in result, we'll get the precise control over the deposition parameters, and it is industrially viable. Few examples are evaporation, sputtering, a hybrid of evaporation and sputtering, that is activated reactive evaporation, molecular beam epitaxy, which is not at all cost effective. It is huge, highly expensive, and it needs heavy maintenance. Whereas on the other case, the chemical route techniques, they are very much cost effective, and they give you high stoichiometry, viable. So here the CVD and the solder based spin or dip coating fall under this category. Yesterday already we have discussed about this CVD and the other chemical route techniques. So I'll be focusing more on the vacuum based techniques, which will give you a more precise control over the deposition parameters, which will result in a better crystalline quality films, and better optical and electrical properties will emerge out of it. So first, let us discuss little bit about the vacuum, why we need it, what is the advantage of using a vacuum based technique, and what are the different pumps and what are the different gauges we generally use in the vacuum based techniques. So what is the advantage of vacuum? So typically the atmospheric pressure is 760 torr, right? So this is the atmospheric pressure. So we have to reduce the pressure, and the generation of the pressure takes place because of the motion of the atoms inside the chamber, atoms of the molecules. They impart momentum to the walls of the container, and as a result, the force is generated, and force per unit area is the pressure. So we have to reduce the number of moving molecules or moving atoms inside the chamber to reduce the pressure. And this is the relation between the mean free path and the pressure inside the chamber. So you can see that at atmospheric pressure, the mean free path is very, very small, of the order of few micrometers or 100 less than micrometer. It is 10 to the power minus 6 centimeter. Whereas when you go for very high vacuum, that is 10 to the power minus 10 torr, this mean free path is very, very large, of the order of 100 kilometers. And when we reduce the mean free path, when the mean free path is very high, in fact, in that case, the collision with the other atoms is very, very low, because mean free path is defined as the distance traveled by the molecules or the atoms in between two successive collisions. So between the target and the substrate, without any collision, it should be able to reach the substrate. The evaporant or the sputtered atoms should be able to reach the substrate. If the mean free path is very, very low, it will undergo repeated collision and it will not be able to reach the substrate. So you have to reduce the pressure so that we can have higher or longer mean free path. That is what is the one of the primary benefits of using the vacuum based techniques. Second one is the avoid any kind of contamination of the film, or the impurity level can be very minimized by creating vacuum. For example, if I keep a substrate in air, we can calculate how much time it takes to generate one monolayer of contamination on it. This is the expression for the characteristic contamination time. So if you see that it is inversely related with the pressure. At atmospheric pressure, within few nanoseconds, it will generate one monolayer of impurity. Whereas, if you go for high vacuum, ultra high vacuum, 10 to the power minus 10 torr, it will take few hours to generate one monolayer of the contamination. So this is the power of the vacuum to avoid any kind of contamination inside on the substrate surface. Another advantage that we get is related with the evaporation. The boiling point or the sublimation point decreases because of the vapor pressure. The vapor pressure is going to be higher. So as a result, the boiling point or the sublimation point decreases. Another benefit is that we can strike the plasma at a very low voltage when we have reduced pressure. Depending on the pressure inside the chamber, we can distinguish the flow of the gas in 2 or 3 different regimes. These are called as and this is decided by the Knudsen number. It is defined as the ratio between the mean free path and the chamber size. So D is the size of the chamber. So if this number is more than 1, then we call it as the molecular flow. That means the gas loses its viscous property and the molecules are only flowing inside the chamber. And the concentration is very low in this case, the number of molecules. So the amount of pressure which they exert on the walls of the chamber also very low. That's why this molecular flow is at a very low pressure, and for which we use certain pumps, which we'll be discussing in more detail. That is diffusion pump, turbomolecular pump, cryo pump, and any other high vacuum pumps. The other extreme is the viscous flow. That means when the Knudsen number is less than 0.01. So here the gas is very viscous. So we have to use the mechanical means to take out the gas outside the chamber. So the example here are the rotary pump, root pump, and many more. Anything in between that, we call it as the intermediate flow. For the intermediate flow also, you have to take the help of the same high vacuum pump. So now, knowing that we have 2 different regimes to take out the molecules from the chamber, outside the chamber, let us discuss briefly about the different pumps. So as I told, depending on the regime, so basic idea in the vacuum pump is to reduce the pressure. And we know that pressure is related with the movement of the molecules or the atoms, which imparts the momentum. So one way is to remove the gas molecules from the chamber to outside, and which is called as the gas transfer mechanism. The other way is to stop the molecules or the atoms from moving. Somehow freeze the atoms or molecules. That is what is called as the entrapment. Both will result in the same effect. And the based on the first principle, we are having 2 kinds of pumps. One is called as the positive displacement pump, and other one is called as the kinetic pump or the momentum transfer pump. And as we know, this positive displacement pump works only in the viscous regime, viscous flow regime. It cannot work in the kinetic or the molecular flow regime. And the example for this are the rotary pump and the Roots pump. Whereas when you are in the molecular regime, this mechanically transferring the molecules from one side to the other side, from the chamber to atmosphere, is not possible. For that, we have to take the help of the momentum transfer pump. The example here is the diffusion pump and the turbomolecular pump. The other way is to just freeze the atoms or the molecules so that they will stop from moving. That is what is called as the entrapment. And the example is the cryopump and the ion getter pump. So let us briefly discuss about these pumps. So as the name suggests, and it falls on the positive displacement category. So in this case, this is the example of the schematic of the rotary pump working mechanism. So here we are having the rotor. This is the stator. So here we can see the gas enters from here, and gradually through the motion of this rotor, it is adjusted out and it is vent out to the atmosphere. So mechanically, we are taking away the gas from the chamber to outside. That is why it is called as the positive displacement type of pump. The other way is to use a root pump. The root pump basically it contains 8 separate lobes. So the shape of this lobes, this is one lobe, this is another lobe. So there are 8 separate lobes are there, and they are rotating at a very high speed. And when they rotate, the motion is such a way that whatever enters inside the chamber, that will be vent out. This is the high pressure exit. That is how the construction is made in such a way that whatever gas molecules or gas enters into this, it is going to be exited out through the proper organized motion of these 8 separate lobes. And both these pumps, they can be used from the atmospheric pressure up to around 10 to the power minus 3 torr, which is in the rough region of the vacuum. Yes, anything? Yes, anybody wants to ask anything? Okay. Valumane?
No, sir, you can proceed.
Okay. So these two are the positive displacement pumps, where mechanically we take out the molecules or take out the gas from the chamber to the atmosphere. Now this is the diffusion pump, which works on the momentum transfer principle, because at lower pressure, we can no more take the gas molecules, mechanically drag out the gas molecules from the chamber to the atmosphere. So what we do is that we transfer the momentums with the help of another high molecular massive molecules, transfer the momentum to the gas molecules, and we vent it out. So here there is a high vacuum pump oil, this is the diffusion oil, which is of high molecular weight and very low vapor pressure. And this vacuum pump oil is heated and it evaporates, and then it goes out, and finally it is going to transfer the momentum to the gas molecules present, and it will be taken out of the chamber. And finally, it is connected with the rotary pump, and through the rotary, it will be adjusted out. And it is always, it runs in conjunction, or it is backed always by a rotary pump, because it works on the principle of kinetic principle, that means the momentum transfer. So this is the mechanism. So when it boils, the gas molecules, they evaporate and they will impart the momentums. Sorry, the vacuum pump oil will be evaporating, which is having high molecular weight, and it will impart the momentum to the gas molecules inside the chamber. And finally, it will be vent out with the backing of the rotary pump. But one of the major demerits of this kind of pump is that it works with the help of the hydrocarbon oil or the silicon oil. So always there is a possibility that this oil will be backstreamed inside the chamber. So the film contamination may take place. To avoid that, we can have an oil-free pump, which is the turbomolecular pump, and it contains a very fast spinning rotor, and the rotation speed of these blades of this turbomolecular pump is around 24,000 to 90,000 revolutions per minute, which is very, very high. And the gas molecules, when they strike this solid surface of this blade, they'll move in a specific direction, and ultimately it will be pumped out of the chamber. And again, since it is a momentum transfer pump, it is always backed by another rough pump, whether it is Roots pump or the rotary pump. So this is one of the advantages of this, is that it is an oil-free vacuum pump. So it can be used for growing high quality films. Mostly it can be used for optoelectronic applications. Then let us discuss quickly about the different vacuum gauges. So vacuum gauges means their primary aim is to measure the pressure inside the chamber. There are three mechanisms in which you can measure the pressure. One is the direct way. Direct way means we can directly measure the pressure. That is, we have to measure the force per unit area. That is what is called as the mechanical phenomenon. So in the mechanical phenomena, it will directly measure the pressure, which is the direct gauge. And the example is the capacitance manometer. The other two fall in the indirect way. That means we'll measure some indirect means which will be affected due to the reduction in the pressure in the chamber. So first one is called as the transport phenomena, because of which there is a change in the thermal conductivity because of the reduction in the pressure. And the example is the thermocouple gauge or the Pirani gauge, which is used for mostly to measure the rough vacuum from the atmospheric pressure up to, again, 10 to the power minus 3 torr. Whereas when the pressure is very, very low, below 10 to the power minus 3 torr, we cannot use the change in the thermal conductivity principle. We have to go for the ionization of the gas. We have to ionize the gas and measure the ionization current, which is dependent directly on the pressure of the chamber. And the example here is the ionization gauge or the Penny gauge. So this is briefly about the different vacuum pumps and vacuum gauges, which we'll be using to either for evaporation or for the sputtering. So now let us discuss about the evaporation quickly. So evaporation, all of us know that basically the working principle is very, very simple. In this case, it involves the condensation of the vapor onto a cooler substrate. We evaporate or we sublimate this particular material. Suppose I want to coat aluminum, then I will evaporate it at a very, I have to heat it at a very high temperature so that it will evaporate from a particular boat, and it will be reaching the substrate, which is placed at a much cooler temperature than that of the boat. And it is governed by the Clausius-Clapeyron equation, that is dP by dt is equal to del H by T del V. Del H is the change in the enthalpy, and the evaporation rate, that is the mass evaporation rate, is given by this. And again, it depends on the pressure and also on the mass of the substance that you are taking in the evaporation boat. There are different ways for evaporation. The most familiar way is to use a filament, which is called as the thermal evaporation, and heat it at a high temperature. It is very simple and very cost effective. You can choose the choice of your filament ware or the boat. And in this case, the one major disadvantage in this case is that we cannot coat any kind of alloy. Suppose I want to coat copper aluminum alloy. And since the copper and aluminum are having different vapor pressure curve, we cannot have an alloy evaporation together. So it will be resulting in more inhomogeneity in the final film. So the alloy formation, the evaporation of the alloys is not advisable using the thermal evaporation. Another disadvantage is that sometimes this material can form an alloy with the boat itself. So you have to avoid. For example, if I use aluminum for the evaporation, I cannot use tungsten boat. It will form an alloy with tungsten and the complete setup will be spoiled. So that's why it is, these are the major advantage and disadvantage. Advantage is that it is simple and cost effective. And disadvantage is that it can result in contamination due to the outgassing from the wire. alloys cannot be evaporated, and we should have to choose the proper boat. The other way is to through the RF induction heating. But again, in this case, the contamination from the crucible, because it is based on the eddy current, so contamination from the crucible can occur. So that also we need to take care. And the best way is the electron beam heating. So, but it is little expensive. You have to use an electron gun for this case. Here we use a focused beam of electrons, and we locally heat only the evaporant. It is not going to fall on the crucible. We locally heat the evaporant, and it is ideally suited mostly for to coat any kind of oxides, nitrites, chalcogenides can be grown using this electron beam evaporation mechanism. Here are the few examples. So this is the growth of zinc telluride thin films by electron beam evaporation. So in the boat, we have taken this zinc telluride powder. It has been kept in the graphite crucible, and using the electron beam, this zinc telluride has been evaporated, and these are grown at different substrate temperatures. And here again, you can see the nice interference pattern in the optical transmittance spectrum, which ensures the formation of the thin films. So at this point, I would like to take a break for 3 to 4 minutes, and I'll be back in 5 minutes. Is it fine, Dr. Devasis, Velumani?
Yes, sir, it is fine. Please take it.
I'll be back at 11.
Yes.
Dear participants, you're kindly asked to wait for other 2 to 3 minutes. We will resume this session after 3 minutes. Thank you.
So shall we start?
Yes, sir, we can.
Okay. So we discussed about the vacuum-based deposition technique. One was thermal evaporation, and also we discussed about the different ways to get the vacuum and how to measure it. So let us discuss about the next type of vacuum-based deposition technique, which is the sputtering. So the sputtering is basically a momentum transfer process, in which case the ions will strike a particular target of our choice, and they will eject out the atoms through the momentum transfer, and then will be going and condensing on the substrate. So the advantage of sputtering is that we can get far better uniformity over a larger size than that of the evaporation, and also it is an ideal technique for the deposition of the alloys. So here is a brief schematic of the sputtering setup. So this is the substrate, this is the target, and we are applying high potential between them, and we are passing an inert gas inside it. The inert gas gets ionized, and the dielectric breakdown takes place, because of which the target is bombarded by the positively charged ions, and the momentum transfer takes place, and the target atoms are sputtered out and they reach the substrate surface. Let us look at it a little more carefully, and let us see how the plasma is generated inside this particular chamber. So basically we are having two electrodes here. One is connected to the negative terminal, other one is the positive terminal, or one can be grounded, other can be biased. So initially we pass argon gas into this or any other inert gas. So let us discuss the step-by-step process of the formation of the plasma. So initially we are having, suppose one electron is there, which is coming from the cosmic background, which is also called as the stray electrons. And this stray electrons is going to act as the primary electron. And this stray electron will be bombarded because it is negatively charged. So it will be going away from this particular electrode and it will strike one of the argon atom. And the moment it will strike, it will eject out one of the electrons from the argon atom, making the argon atom ionized. So now we are having this argon plus. In return, now we are having two electrons. We started with one electron. After ionization, we are having two electrons. And these two electrons will act as the source of the ionization of the another two argon ions. And this will be a cascaded process. So in each process, we can have two electrons like this. And ultimately, we are having a collection of electrons and charged ions, positively charged ions. And this collection of electrons and positively charged ions together with the neutrals is what is called as the plasma. And the argon ions will be attracted towards the negative target and the electrons will be towards the positive terminal of this particular setup. Having said that, let us look at few important properties about the plasma. But more about this will be discussed in our next session by Dr. Rakesh Maulik, which is scheduled at 11:30. But I'll be discussing few important characteristics of the plasma, which we use in the sputtering. So basically, plasma is it is defined as a quasi-neutral gas. It contains the ionized and neutral particles, and the behavior is collective. So let us try to understand what is the meaning of this. Quasi-neutral means up to certain range of the order of d by length. One parameter is called as d by length, within which the charge separation of the ions and electron take place. And it is around few tens of micrometers. So up to this, it is not neutral, but outside this, the plasma behaves as a neutral gas. And since the Coulombic interaction is long range in nature, that's why even though the charge localization takes place in a very small region, but the impact is there to a larger distance. That's why the collective property or the collective behavior emerges. So basically, plasma is a quasi-neutral gas of ionized and neutral particles. There are very synonyms for this plasma which we use in our thin film processes, that is basically sputtering. So the different synonyms are cold plasma, glow discharge, non-equilibrium plasma, and low pressure plasma. All these stand for the same thing. That is what we are going to use in the sputtering. So let us try to understand or try to have the idea about the ionization degree. The degree of ionization is defined as the density of electrons or ions divided by the density of the neutrals that is present inside the particular plasma. And the density of electrons and ions are going to remain the same because whatever is ionizing is coming from the electrons. So Ni is always equal to Ne. So both the densities are going to remain the same. And for this low pressure discharge, which we use for sputtering purpose, the degree of ionization is very, very small, around 10 to the power minus 6 to 10 to the power minus 3. For magnetron sputtering, at around 1 millitorr, it is between 10 to the power minus 4 to 10 to the power minus 2. So you can have this definition and see these numbers. Okay, so it is basically how many electrons or ions are present inside the plasma. That is what is given by this. So, or indirectly, it will give you an idea about how much the atoms or molecules are being ionized. And why it is called as cold plasma? If you look at any plasma, it is having different temperatures. One is the electron temperatures, because depending on the species, it is having the different temperatures. Ion temperatures, the temperature of the gas, temperature of the chamber walls. There are different temperatures, and all are different. None of them are equal to each other. When at very low temperature, very low pressure, we can see that the electron temperature is very, very high, because in this case, the number of electrons are very high compared to the, the number of electrons moving is very, very high compared to that of the number of ions. So even though the temperature is very, very high, 10 to the power 4 Kelvin for the electron, but the electron heat capacity is very, very low, and the density of electrons also very, very low. So the amount of heat that is transferred by the electron to the rest of the system is very less. That's why the plasma is not hot. It is at the room temperature, and therefore it's called as the cold plasma. So here we should make a note that the electronic temperature is very large compared to the gas temperature, and it is happening at a very low pressure. That is what we see in the sputtering process. And there is another important thing that we should note down, which is called as the dielectric breakdown. When we apply a potential difference between the two electrodes in the presence of an inert gas, the gas starts to conduct after a certain critical voltage, and that voltage is what is called as the dielectric breakdown voltage, or the breakdown voltage. And it follows the Paschen law, which is APD by a ln of PD plus B, where D is the distance of separation between the electrodes, P is the pressure in the chamber, and A and B are some constant coefficients. And these are the typical Paschen curves for different inert gases and that of the air. Here we can see at a low pressure, the breakdown voltage is very high. At high pressure also, the breakdown voltage is very high. So at low pressure, what happens? The number of electron-ion collision is very, very small, and the small ionization is not able to sustain the ionization or sustain the plasma. On the other extreme, at high pressure, what happens is that the number of electron-ion collision is very high, so the electron cannot acquire sufficient. So you have to find out one optimum range for the breakdown voltage, which occurs in between around few tens to the few hundreds of volts. So this is what we have to look into according to the Paschen curve. During the sputtering process, when the ion is going to impart energy to the particular solid surface, only for a certain optimum energy of the ions, the sputtering takes place. So this is the graph between the sticking probability versus the kinetic energy of the ions. So sticking probability is defined as the number of ions that is sticking to the target to the number of ions which are injected into the, which are impinged onto the target. Suppose I am 1000 ions are bombarded onto this target. Out of this 1000 ions, suppose 100 ions are they are impinged onto the target. Then the sticking probability will be 100 by 1000. Typically, at a very low energy, all the ions, they will be condensed or they will be adsorbed by the target surface, which is not desirable because they should be able to extract the atoms. At low energy, this is not possible. Okay, so basically the ions should have typical energy of 10 to the power minus 2 to 10 to the power 4 electron volt for the sputtering mechanism to take place. Another important characteristic for the sputtering is that the sputtering yield. Not all the materials are having the same sputtering yield. That means sputtering yield means the number of atoms that will come out or that will be ejected out of the target surface when one ion will strike the target. Here we can see, for example, for silver and copper, the sputtering yield is very, very high, whereas that for titanium or carbon, the sputtering yield is very, very low. So depending on the sputtering yield with respect to a particular sputtering gas, we should be deciding the deposition time. Now let us look at the different variants of sputtering. So basically there are 4 variants, that is DC sputtering, AC sputtering, reactive sputtering, and magnetron sputtering. But most of the times we can have an intermix of this kind of different variants. For example, there can be DC magnetron sputtering or DC reactive magnetron sputtering, AC reactive magnetron sputtering. So there can be a combination of these different variants of sputtering. Under the DC category, we are having 2 things. One is the diode sputtering and the triode sputtering. For the AC, we are having the pulsed mechanism, and other one is the RF mechanism. And the reactive and magnetron sputtering are mostly superimposed on this DC and AC sputtering. Now let us quickly look at the different variants. So all of us know that the diode sputtering will require very high pressure for the discharge or the plasma to be sustained. So the breakdown voltage is very, very high in this case. So it is typically more than 10 milliliter. And the typical breakdown voltage is few kilovolts. And it will result in a very low ionization current. And when the current density is very, very low, the sputtering will be low. So the sputtering yield is also going to be low. So to avoid these demerits, we can go for the triode sputtering, which will enhance the degree of ionization. In this case, together with the conventional target and the substrate, we are having another electrode, which is called as which will act as the supplier of the electrons, which is the thermionic emitter. So this thermionic emitter will supply more electrons. As a result, the gas ionization will be enhanced. But the major disadvantage of this technique is that the plasma in the chamber is not uniform. So it will result in a non-uniform plasma density. And as a consequence, the target surface will not be uniformly etched. It will be resulting in the uneven erosion of the target surface. So to avoid all these things, we can go for the magnetron sputtering, so which is most widely used and it is industrially viable. In this case, we apply a magnetic field to the target in a perpendicular direction. So the Lorentz force, it will enhance the ionization efficiency, and also it will reduce the operational pressure and the breakdown voltage. The current density, since the effective ionization takes place in this case, the current density is very, very high, around 100 milliampere per centimeter square. And the plasma can be sustained even at a very low pressure of typically 2 milliliter or less than that. The breakdown voltage is typically few hundreds of volts for a typical sputtering chamber. So this is the most widely used and it is industrially viable. But one problem with this DC magnetron sputtering is that the poisoning of the target when you are going for the reactive sputtering. In the reactive sputtering, what we do is that the metal target is sputtered in the background of another reactive gas, for example, oxygen. Suppose I want to go for the zinc oxide thin films. I will sputter zinc in the presence of the argon and oxygen gas. Argon is going to act as the sputtering gas, and oxygen will be acting as the reactive gas. But slowly, as the sputtering process progresses, the oxide layer will be formed on the target surface, and that is what is called as the target poisoning. Together with that, if I want to directly coat the higher impedance materials, for example, the transparent conducting oxide using a single target, it will result in the charge accumulation at the target surface. And when the charges will accumulate, that will result in an arc. Arc means very high density of currents. And when the arc is generated, so it will split the target atoms at a very high speed, and it will result in a very poor quality of the films. So to avoid the formation of the arc due to the target poisoning, or when I want to use a single high impedance target, we have to go for the pulsed DC process. In the pulsed DC process, the target poisoning is neutralized by applying a negative bias at a frequency which ranges from few hundred to few kilohertz, depending on the need or depending on the geometry of the particular sputtering chamber. It can be between few hundred to few hundred volts to few hundred hertz to few kilohertz. And in the reverse bias, when it is applied, it will remove any kind of charge accumulation at the target, and it will result in the neutralizing the poisoning of the target. So this is what is mostly followed in all the industry for coating the metal oxides. The another way, which is having low feed through, but which is an excellent way to coat the insulating thin films, is through the RF magnetron sputtering. Here, remember, we are going to use very high frequency. In pulse DC, we are going to use few hundred or thousands of hertz, but in this case, we are going to have more than 1 megahertz of frequency. At this high frequency, what happens is that the electrons, which are lighter, they can easily respond to this rapid change in the polarity, because it is 10 to the power minus 6 seconds, they have to change the polarity. So electrons are very lighter and they can easily respond to this change in the polarity, even though it is very fast. But on the other extreme, the ions, which are very, very massive, they cannot respond to this rapid change in the polarity. And due to this, the target is self-biased. Target self-biasing takes place to a negative voltage. And this self-biasing of the target will stop any kind of charge accumulation, and it will attract only the positively charged ions, which will result in the effective sputtering. But one of the demerits of this RF sputtering is that this RF plasma, it is going to cover the complete volume of the chamber because of the change in the rapid change in the polarity. So both the electrodes will start to sputter, which is not the case in case of the DC plasma. DC plasma, it is only confined to the target or the cathode. So the solution to this is that we have to have the target size very small compared to that of the chamber size, because the voltage, the self-biasing voltage for the target is inversely related with the area of the particular electrode. If we have a very large chamber, inside that we are having a target which is of very smaller size, then we can avoid the sputtering of both the electrodes. That is what is the basic principle of the RF magnetron sputtering. It is a popular technique to grow the insulating thin films through the use of a single target. Then finally, I'd like to discuss one of the hybrid between the evaporation and the plasma process, which is called as the activated reactive evaporation. In this case, what we do is that we evaporate the particular material. Suppose I want to coat zinc oxide again. So I'll evaporate metallic zinc. So this is the evaporation source. I'll keep the metallic zinc here, and I'll create an oxygen plasma. So this is the oxygen plasma. And I'll put the substrate here. Now the zinc will readily react with this oxygen plasma because it is already in the excited state, and it will form the film on the substrate. So this is what is called as the activated reactive evaporation, which is a hybrid technique of the evaporation and the plasma-based approach. So now quickly we'll discuss using the vacuum-based techniques how to fabricate or deposit the different layers of a solar cell. Here I have taken the example of the CZTS based solar cell. That means copper, zinc, tin sulfide is going to act as the observer layer. The back contact is moly-coated glass substrate. The window layer is zinc oxysulfide. The top contact is aluminum doped zinc oxide. So whatever the techniques we have learned till now, using those techniques, let us see what are the possibilities to coat these different layers. So first we'll start with the back contact, that is molybdenum metal. So it can be done with thermal evaporation or with e-beam evaporation or with the DC magnetron sputtering. It is simply a metal, so there is no use to any kind of reactive sputtering in this case. Now coming to the main layer, that is the copper, zinc, tin sulfide, which is a quaternary compound. It contains copper, zinc, tin, and sulfur. So what we can do, we can have a very big vacuum chamber, and we can co-evaporate all the constituents together in a very controlled manner. We can have a source for copper, another one for zinc, tin, and sulfur. We can evaporate them, we can monitor the evaporation rate, and we can allow all of them to react on the substrate surface to form the copper, zinc, tin sulfide thin films. The other alternative is to go for the DC reactive magnetron sputtering, where we are going to use the co-sputtering technique, where we are going to have these three targets, copper, zinc, and tin. They are the different targets which are connected to the DC power supply, and all are magnetron sputtering. And we can sputter it in the presence of the S2S plasma. So the plasma will be argon plus S2S. S2S is going to act as the reactive species in this case. So it will supply, it will act as the source of the sulfur, and ultimately will end up in the copper, zinc, tin sulfide. But again, S2S is very toxic, so, and it will corrode the chambers and all. So we have to look at it with a very precise way. We have to do this. And the most, the better way is to go for the RF magnetron sputtering. So where you are going to use a single copper, zinc, tin sulfide target, but the limit that you are getting here is that there are not enough parameters to play with the stoichiometry. So everything is already present in the target. So we cannot change the stoichiometry of the target, which will result in the films. Another way is to go for 3 RF co-sputtering. You take or pulse DC sputtering. You take the materials copper sulfide, zinc sulfide, and tin sulfide. Here you are going to have 3 different controls, and you can have the CZTS films. But the best control you will get here, the worst control here. But you have to pay the price with the S2S plasma. So more is the deposition parameters, more is better will be the control of them. Now coming to the window layer, which is kind of alloy of zinc oxide and zinc sulfide, just called as the zinc oxysulfide. So the first method is to take a single target of zinc oxysulfide and go for the RF magnetron sputtering. Straight away you can have this zinc oxysulfide, but the major limitation is that you cannot change the oxygen and sulfur concentration. Whatever is fixed in the target, the same you can expect in the film. The another way is to go for the reactive RF magnetron sputtering of zinc sulfide with oxygen as the reactive gas. Here you can change the concentration of oxygen, and you can tune the alloy constituents. Another way is to go for the pulsed DC reactive magnetron sputtering of zinc plus RF magnetron sputtering of zinc sulfide. So here the reactive gas is oxygen. We have chosen pulsed because it will poison the target. It will become zinc oxide insulating layer. So you have to regularly take it out using the pulsing mechanism, and the sulfur source will come from the zinc sulfide. And finally, another way is to go for 2 RF power supplies and 2 magnetron targets, that is zinc oxide and zinc sulfide. Finally, the top layer is the aluminum doped zinc oxide. Here the popular way is to go for the single layer the single target, that is aluminum doped zinc oxide. You can buy it and you can directly use the RF power supply to coat the AZO fins. Otherwise, is to go for a pulsed DC reactive monotone sputtering of zinc and aluminum in the presence of the oxygen plasma, oxygen plus argon plasma. You can go for it. So this is just a small example through which you can fabricate the entire solar cell through the vacuum-based deposition technique. Now let us quickly discuss about the current status of thin film-based solar cell. I will go through it quickly, another 2 to 3 minutes. So we know that the detrimental effects of the non-renewable energy sources are they're hugely impacting the environment. So the focus has naturally shifted to the renewable energy resources, and out of that, the solar power has gained significant interest in our country. We can see that there is around 13-fold increase from 2014 to 2020, from 2.6 gigawatt power generation capacity to around 33 gigawatt power generation capacity by the end of 2019. At the current scenario, if you look at the international scenario, so it is estimated that by 2030, around 2.8 gigawatt power installation capacity will be generated throughout the world. Currently, 2-3 years ago, it was around 480 gigawatt. So that is a huge expectation. And mostly silicon is being used. Silicon is the leader in the solar photovoltaic market, but the cost effectiveness of the silicon photovoltaics is very, very limited. So the interest is gradually shifting towards the thin film based photovoltaics. So this is the few data about the thin film based photovoltaics. So this yellow is for the thin film based photovoltaics, and this blue color, the dark blue, is for the multi-crystalline silicon, and this light blue is for the single crystalline silicon. So you can see the market trend, how it is fluctuating day by day, and thin film based photovoltaics is definitely has got an impact on it. The different materials which are used commercially for the thin film based photovoltaics are amorphous silicon, cat telluride, and copper, indium, gallium, sulfoselenide. You can see the trend, and you can see the trend for cat telluride in around 2009 or 2010. But now the cadmium toxicity is a major issue. So we have to get rid of the cadmium telluride based solar cells, and CIGS based solar cells are not that much cost effective because of the involvement of indium, and amorphous silicon, there are some stability issues. So there is a challenge to go for the alternatives beyond this conventional thin film based solar cell. So there are the efficiencies of few conventionally used solar cell, either in the research scale or in the commercial scale. You can see that the crystalline silicon, the efficiency is reported to be around 25%, whereas for CIGS, it is closely in match with that of silicon, around 23%. Cat telluride also around 23%. CZTS and CZTS selenium is around 11 to 12%. The perovskite based solar cells, which are only in the lab scale, it is also around 23%. So you have to go for this kind of comparison, and the research will progress along this direction. So this is again the same table in a different way it has been presented. Amorphous silicon, the efficiency is limited to 11 to 14%. Thin films is again the same case, but you can see the major difference between the modules and the cell. When you prepare a module, definitely the other kind of resistance also come into picture. So the module efficiency is always smaller than that of the cell efficiency. And silicon is the leader, as I told, with the highest efficiency of around 25 to 26%. So this is the current scenario for the thin film solar PV market. Remember, it is only the thin film, it is not the complete solar PV market. So here you can see in Asia, it is having a huge impact compared to other African or South American countries. In North America also, it is having some moderate impact, but especially in Asia and Australia, it is having huge impact. So with this map, I would like to conclude my presentation. I would be happy to take any questions or any kind of interaction.